Antibiotic resistance is going to be the main challenge for us within the next few decades.
Antibiotic resistance is already killing millions of people globally each year.
We may even not be able to perform certain cancer treatments and surgeries because of the risk of death due to drug-resistant infections.
It's a race. We come up with new solutions with new bioactives, and the microorganisms try to find ways of dealing with it.
We found a lot of useful drugs.
Most of the ones we use, we discovered earlier, mostly from soils.
But that pipeline's sort of run out a bit now. So we need to develop new ways of discovering antibiotics.
There's a huge range of potential for AI to speed up and streamline that process.
So my interest was in antibiotics, was looking for new antibiotics that would replace some of the antibiotics that microorganisms have become resistant to. Some of my colleagues were looking for new antibiotics in exotic environments. So they were looking maybe in the Gobi Desert. And about 2015 I started to look at some of the organisms in the soil and found that there was a lot of antibiotic-producing microorganisms. And that's when one of the local people told me about this cure from Father McGirr. Just now we're in the graveyard of the Sacred Heart Church in Bow, which is in Fermanagh. So it's a kind of highland district. It's kind of a long history. Father McGirr died more than 150 years ago, and he was kind of the local folk healer at the time. And he said that after he died, that the soil that covered him would heal the same things that it healed when he was alive. And this has remained a site for people to come and collect soil for a curative effect. Somebody told me about it because they knew I was analysing some of the soil and I was looking for microorganisms. So they said, you know, what about testing this soil we have in Father McGirr's grave?
Okay, just clap for us. Perfect.
My name is Jerry Quinn and I work in the University of Ulster, and my specialism is streptomyces or metabolites from streptomyces, which include antibiotics.
And what did you think when you first started being a scientist?
So, you know, when I heard about the folk cure, I thought, yeah, maybe. You know, I wasn't 100% convinced that, you know, but I thought, well, if it's in most of the other soil in the surrounding area, then we might find a few exotic streptomyces in the Bow soil. Streptomyces, after penicillin, which didn't cure everything, they were looking for more robust antibiotics to cure tuberculosis, and that's when they discovered streptomyces. And streptomyces produces streptomycin, which cured TB. And then after that, which was called the golden age of antibiotics, which lasted about 40 years, many other antibiotics were discovered from streptomyces, like tetracyclines, chloramphenicol, and neomycin, and other antibiotics. I was slightly sceptical about the cure at the time, but I also thought, well, you know, I could test this cure in my lab and see what's there. Basically, we took a sample of soil. Conveniently, there's some implements, but just a small sample of soil. Okay. And then we put it into a sterile container. Okay, that should be on there actually. And then we bring it back to the lab. This is some of the soil that we took from the graveyard sample here. Okay, and then we're going to see what kind of microorganisms it contains. So we prepare a specialised media. So sometimes with environmental samples, We actually take a sample of the environment round about, and then we make our own homemade agar with it. So agar is a semi-solid substance that's useful as a growth media, and most bacteria will not digest agar, so we can grow it on top of an agar surface like this. Okay. And then this media is able to grow the selective organisms. So you can see in this one, the agar has been able to select out some of the streptomyces. So from this type of plate, we're able to subculture the streptomyces and make a pure culture. Okay, this plate here. This is actually Streptomyces myrophoriae. Okay, and you can smell the myrophoriae. You can smell the incense type smell. So we core out these. We make a core of the agar that might contain antibiotic or the secretions from the organism, and then we test its ability to inhibit some multi-resistant pathogens, like this one is Pseudomonas aeruginosa. This Streptomyces myrophoriae was one of the 7 organisms, the 7 strains of Streptomyces we found at the grave. This particular one actually had the most inhibitory activity. You can see some of the inhibitory activity here. Okay, we can see some zones of inhibition against a pathogenic strain of bacteria. When I published these results, the reaction from the scientific community was, yeah, that's cute, a discovery, like a fluffy dog story at the end of the news, or a dog that can talk. But I was more interested in finding what the antibiotic was, or even the potential for finding a new source of streptomyces, which is really what we're looking for. We're looking for new antibiotics. So if we find old or ancient healing sites contain streptomyces, that would be, it'd be a great discovery, I think.
And what did you think when you first heard about Jerry's work looking at soil samples from Father McGirr's grave?
Well, I thought first of all, you think, oh gosh, is this far-fetched type approach, until he pursued it and actually managed to isolate some new microorganisms with the capability of producing antibiotics. So then say, okay, there might be something there, and then he pursued it, and we published a couple of papers together in a review on this area of antibiotics and of the new isolate that he discovered. It's different. It's thinking outside the box type thing, which is we always try to encourage whenever we can. My name is Ibrahim Banat. I am a professor at the University of Ulster and the School of Biomedical Sciences. We really need solutions. We need governments to support research and finding new antibiotics and taking them through the whole gamut of tests to make sure that they are ready to reach the market, which costs millions of pounds and could take maybe up to 5 to 10 years sometimes for each individual kind of new discovery.
And one thing we hear about a lot these days is AI. Do you think that this could be a useful tool in this space for antimicrobial resistance?
AI is a useful tool in everything nowadays. We find that there must be some aspects, particularly for testing, designing experimental procedures, or different types of testing, reducing that time span that it takes for getting something from discovery to market. Yes, of course.
But the other thing about AI is it's based on current knowledge. So it gets a bit difficult when you're at cutting edge knowledge and you're finding new compounds and they're not in any database.
I think that AI will provide a potential avenue for reducing the costs of new drug development. There's a huge range of potential for AI to speed up and streamline that process and help us make better choices about which drug candidates we can carry forwards to investigate.
So AI can be very controversial. It's clearly, used sometimes for really unpleasant purposes. But AI also has tremendous potential for good. AI is great at looking at complex data and helping us reach decisions and learn things very quickly, so it can help develop new antibiotics. What it's really useful at is looking at really complex data sets, find patterns, and generate useful, usable information that we can take and apply that to make better antibiotics more efficiently.
Can you just give us a little clap, old school? Okay.
Great. Ready to rock and roll.
Let's go. My name's Dr. Andrew Edwards. I'm an Associate Professor of Molecular Microbiology here at Imperial College London. I study antibiotic resistance, how bacteria become resistant, a bit about how antibiotics work, and then the main focus is how we can make them work better. So one of the big challenges with antibiotics is when it comes to a group of organisms called gram-negatives. And they're particularly problematic because they essentially have a very complex outer layer that's very hard to get drugs past. So one of the things that we're doing here is to try and understand what are the chemical properties that we can use to trick the bacterium into allowing antibiotics to get through that complex outer layer. And so what we're going to do is throw tens of thousands of different chemicals at bacteria and then use really, really clever bits of equipment like this Agilent Rapid Fire behind me to figure out which ones can get in, which ones can't, and then use some very complicated artificial intelligence to tell us these are the chemical tricks we can use to get new antibiotics into the cell and develop a whole range of new antibiotics. So an important thing to remember with AI is that it works well when it has lots of data. If you think about something like ChatGPT, it works well because there's the sum total of human written text on the internet across lots of different languages. When it comes to antibiotic research, there's not that much data to build the AI models on. And generally speaking, the more data we have, the better the models. So a key challenge for us with this project is to generate lots and lots and lots of data across a diverse chemical library to understand which chemicals get in the cell, which ones don't, and then understand the differences. So to generate lots of data, we need a very high throughput system. And what we have here is an Agilent Rapid Fire machine that allows us to process a sample every 10 seconds. So what we do fundamentally to generate the data is we grow up a lot of bacteria. We take a 384 well plate, so lots of little wells in a plate. We add bacteria to each one, and each well will have a different chemical added to it. We'll let it equilibrate. Then we wash off any of the chemical that didn't get into the bacteria, and then we smash those bacteria open. We use very high-tech equipment to detect and quantify the presence of each chemical and tell us which ones got into the cell, which one didn't, and that will help guide antibiotic design in future. This project is a new one here. We're just getting started, but I think what's important to say is that we're building on the work of various other groups around the world, and there's enough work done so far to give me enormous confidence that we're going to learn lots and lots of useful tricks that are going to help us support the development of next generation antibiotics. At the moment, we're not developing nearly enough to keep up with resistance. Bacteria are several steps ahead of us. And this isn't something that is going to be fixed if we get 5 or 10 drugs. This is something that needs to happen for a long time. So in addition to developing new antibiotics, supporting the development of new antibiotics, what I hope for this is that we support colleagues around the world, industry and academia, to develop a sustainable pipeline. That means we will be able to keep developing new drugs over time. That means we will always have enough to sustain other areas of medicine that rely upon them.
So my research predominantly focuses on the optimization of antibiotics. So it's a way of trying to make the lifespan or the shelf life of those antibiotics last and ensure they remain effective for as many people as possible, both now and in the future. My name's Tim Rawson. I am a Clinical Associate Professor in Infectious Diseases and Antimicrobial Resistance, working with the Fleming Initiative at Imperial College London. So the development of new antibiotics is one of the important approaches we can take to addressing the problem of antimicrobial resistance. But what it doesn't do is address that core underlying problem we have of physicians and prescribers overusing and misusing agents, And as we see at the moment, as we bring new drugs online, we rapidly see the emergence of resistance to them within our bacterial populations which we're targeting. And so as well as developing new drugs, it's vital that we develop better ways of diagnosing infections and then better ways of delivering antibiotics in an optimal way, which prolongs their lifespan and stops the emergence of resistance earlier than is necessary. In trying to help us optimize antibiotic prescribing, one of the ways that's widely being investigated at the moment is using a subset of artificial intelligence called machine learning, which essentially can be used to develop prediction models that take in patient and healthcare data, apply it to that individual person, and make a prediction about, for example, the likelihood of them having a resistant infection or the likelihood of them deteriorating based on a decision that we make today. What this allows us to do is utilize all of that healthcare data that's available to us to make more precise decisions and actually make the most of that information that's available that individual clinicians may not have time or the skill to be able to interpret in isolation. The way it works is not by replacing the doctor or the clinician making a decision, but helping augment their decision making. So currently we have clinical decision rules that doctors use to make decisions about, for example, antibiotic prescribing, the risk of deterioration and death, or whether someone needs to, for example, go to the intensive care unit or not. What artificial intelligence tools do is they are trained on large amounts of data, often from healthcare settings, and then when presented with a new patient's information, they try and make a decision about what category or what risk categorization that patient falls within. That information can be presented back in an interpretable fashion to the clinician and then used as part of their wider decision making to make a decision about what antibiotics to prescribe or the risks to that individual patient.
And so, have you had much success with this so far?
So our group have been researching the role of AI to support clinical decision making for over 10 years. We've developed a number of different AI tools to support a range of different decision points, and we've been able to test these in clinical practice and demonstrate the impact they have on antibiotic prescribing. The next steps for us is to take these to a broader level beyond single hospitals and apply them in clinical trials to understand their true effectiveness in the real world.
My hope for this research is to discover new antibiotics. Researchers have been looking for new sources of streptomyces in extreme environments, but if we find environments that are closer to home, like spiritual healing sites or something, in extreme areas, or not sites that are not generally considered too extreme, then that will be a lot easier to isolate the streptomyces rather than going all the way to Antarctica to isolate a new bacteria.
As I said, it's a race between us and the microorganisms, and we have to be ahead of them, at least one step ahead of them.
My hope for the future is that we'll be able to improve the way that we use antimicrobials and help improve outcomes for patients with drug-susceptible and drug-resistant infections. And I think that a large part of this is going to be supported by the rapid developments we're seeing in artificial intelligence across a range of different settings in infectious diseases.
One of the reasons I enjoy this job is because it's a big challenge, but I think it's one that is solvable. I think I work with lots and lots of very smart people who are, working in AI and chemistry and in the clinics. And I think by working together, with our partners in industry as well, this is solvable. We can actually do something really, really useful here. That's not to say that there aren't going to be a huge number of challenges, but I am an optimist. I think we can solve this problem, and I think we're starting to do that.